Hello, good morning. So, we in earlier chapter we studied the designing of the spillway, the part 1. Now, we are going to continue the design of the spillway, the part 2. So, here we cover some of the basic concept and also the design problems that we completed partly at the design problem 1. So, here we designed a component 3, that is chute or the discharge carrier, that is one of the component of the chute spillway. So, here we have to calculate the critical depth. So, critical depth is calculated using the discharge of the spillway and the length of the spillway using this equation. So, Y c or the critical depth, as you know from the principle of fluid mechanics, it is a quadratic square root and q square upon g, and this comes out to be 8.77 meter. Now, the depth at the top of the spillway was calculated to be 4.2 meter, that is based on the slide 17 in design problem 1. So, this 4.2 meter is less than the critical depth. Hence, the flow at the top of the spillway is supercritical. The chute channel or the discharge carrier should now be given a milder slope for a little distance from the toe, but in no case this should be less than the critical slope. So, the flow remains to be a supercritical. Then the critical velocity V c is q, the critical discharge, divided by Y c, which is the critical depth. So, this is the critical discharge is 80.7 that we calculate in earlier step, and Y c, this one, is around 9.18 meter per second. But what we know from the this one from the flow in a channel. So, this relation V equal to 1 upon n r to the power 2 by 3 s to the power 1 by 2. So, we plug everything here. So, a rectangular channel with a bottom width of 62 meters should be provided at a chute channel for the chute spillway. So, at a critical flow, so this is the area of the channel. So, B into D. So, we calculated from earlier step this B, that assuming the channel as a trapezoidal and a critical depth as 8.77, and weighted perimeter, we calculate again the weighted perimeter, which is again B plus 2D. We calculate here. So, the hydraulic radius is A by P. So, we everything going to plug into the equation. So, we everything plug going to plug here into the equation. So, we calculated the weighted perimeter and the area of the channel cross section. So, now the critical slope, we like this we calculate the critical slope here. So, which is 1 upon 428 as a reverse curve. A slope of say 1 upon 250 is to be provided at a 25 meter distance from the top of the spillway. Since the critical slope is come out to be 1 upon 428. So, we gave a distance of 25 meter at the top of the spillway, and then we provide a slope of 1 upon 250. So, bed level at the end of this slope is 190.4 from earlier calculation in design 1 divided minus 25 by 250, a 190.3 meter. A reverse curve at the toe may have a radius equal to twice h e, which is twice, and h e was calculated from previous step. So, it is around 27.5 meter. Now, we have to construct a table for the design problem. So, from this point onwards, a relative level of 190.3 meter and up to relative level of 103 meter, the slope of a discharge carrier may be steeped depending upon the site contour. A slope such as 8:1 to 4:1 may be given in the initial stage, and then a steeper slope say 2:1 and 3:1 is to be given. So, the given design is like a rectangular channel. Whenever the slope is changed, the transition curve, as we learned earlier, the convex or concave in shape may be designed. In the given question, since the site contours are not known beforehand, so we shall assume that a slope of 6:1 is given for first 21 meter fall, like up to relative level of 169.3 meter, and then a slope of say 2:1 is given for the rest of the ridge. So, like this we have to construct a table where calculation of water depth of the chute channel or the discharge carrier is to be solved. So, this is in a slope of 2:1, and then this is we again we calculate using the our assumed value, and here we the column 18, the actual tail level. So, we compare the value at column 10 versus column 18. So, in the next slide we explain this. So, at the depth velocity etc at the end point of 1 in 250 slope may be taken to be same as they were at the toe of the spillway, because the small length of 25 meter shall produce much difference. So, with this assumption that tail at the starting point of new slope 6:1 is equal to 213.21 minus 0.1 meter, that is 213.11. Now, the calculation of water depth, velocity etc. now can be carried out for entire ridge. So, the relative level of 190.3 to relative level of 103 meter of the discharge carrier, and now we divide the entire channel length into small reaches. So, we divided the entire channel length here in the small reaches, say at an interval of 42 meter, and we calculate each of this quantity, the velocity head, specific energy, and we compare this with the column 8, the actual tail water level. Now, the column 18, as I explained earlier, is then compared with column 10, and they should approximately equal. If the difference is large, then the assumed depth is changed till equivalence is maintained. So, it is a trial and error procedure, and once this one set that the actual level is similar to the calculated level. So, our design is almost accurate. So, here you can see at the last end of the channel, means we divided at a small interval 42 meter. So, at the end, so the column 10 is approximately equal to column 18. So, now these our assumptions are correct. Now, the design of curve number 1 at the junction of 250.1 and 6:1 slope, since the slope is now from steeper to milder, a convex curve shall be provided. So, the convex curve is designed as per the equation. So, this was the equation given earlier, and k is assumed as 1.85. So, which is also given in slide 18 in chute spillway design part 1, and d plus hv is the specific energy at the junction point. Hence, the specific energy, as you know, it is given by the d plus v square, the kinetic head. So, we plug it here, and tan phi is the angle, the slope of the angle of the floor upstream of the junction point, which is the slope 1:250. Now, since the tan phi is very small, now cos square phi is also approximately unity. Since tan phi is here, is 1 upon 250, cos phi is also we can approximate as 1. And here you get a convex curve, and then the slope profile is so we plug everything here. So, we get here x tan phi is 1 upon 250 in this case, x square 1.5, and we assume this one also as unity. So, it is void down to this form of the equation, it is a quadratic equation. Now, since we are dividing the channel reach into small sections, so we differentiate y with respect to x. So, we get a dy by dx, since it is we differentiate it is 2x, and then we get into this form of equation. The curve meets the downstream slope where dy by dx is minus 1.6. The negative sign shows that as x increases, the y also decreases. So, we plug it here. Sorry, this thing will be 2x. It is a small correction. So, it will be 68 point something. This is a small correction here, please note. So, we plug it everything here and we get the value of x as 11.3 meter. So, other coordinates of this curve for values of x is between 0 to 11.3 meter is determined based on this equation. So, y is negative of course. So, as given below in the table 5. So, it comes out like this. Now, the design curve number 2 at the junction of 6:1 slope and 2:1 slope. From table 4, the specific energy at this point is found out to be D plus HV, that is 38.75 meter. Now, since tan phi is 1 by 6, the cos phi is approximately 1. So, y equal to minus x by 6, we plug everything here and we the equation and then after getting y value, we differentiate with respect to x here. So, it meets the downstream slope at slope of 2:1, and since dy by dx is minus 1 by 2, we solve it like this. So, it comes out to be 38.75 meter. So, this portion here. It means that the convex curve shall become a tangential to the slope of 2:1 after traversing a distance of 38.75 meter. The coordinates of this curve can be found out from x equal to 0 to x equal to 38.75 meter using this equation, and the values are shown in table 6. So, this is the value are shown in the table 6 at x equal to 0 meter, what is the corresponding value of y. So, y will be in downward shape. Now, the position of the Stirling basin for energy dissipation by hydraulic jump. From table 4, the depth of the tail water level, so D equal to 2.015, F is Froude number and F1 is 9 meter. So, provide the basin tail water depth 50% more than the conjugate depth as you remember y2 and y1 both, as the Froude number is large at a depth 1.05 into y2. So, we assume that we designed the tail water depth as 50% more than the conjugate depth or the y2. So, 1.05 of y2. So, y2 is 24.7, and if I increase it 50% more, it will be around 1.05 of this. So, it will be around 26 meter. Hence, floor level of the jump basin is 103 minus 26, that is 77 meter, and USBR steeling basin is to be provided here. So, this is the complete design. So, first we designed the profile this one, and then the control structure or the UGI wire, and then we put a convex curve here at a slope of 6:1, and first convex curve, and then we provide a second convex curve at a 6:1, and this is the curvature and the slope of this convex curve is shown here. So, this complete your design chute spillway. Thank you.